So our idea here is that to write that out, that E2G times AU has to, because of these functions, has to equal E2U. Well, we know what E2U is. We just calculated that. We know what AU is, and so we just have to divide by AU and divide to figure out E2G, the last one. And AU is just ones and negative ones. Well, dividing by 1 or negative 1 is the same thing as multiplying by 1 or negative 1. So this becomes really easy. We can just multiply them or divide, however you want to think about it. But E2G is going to be equal to E2U times AU. And AU is a really nice one, right? Because it's ones across the board all the way for the first 6 classes and then negative 1 on the other 6 classes. So we just have to take E2U, keep them the same for the first 6 classes. 4, 5, and 6. And then take the negative of them for the remaining classes. And this makes sense because for inversion, we should get a G, and 1 plus 1 equals 2 there. And so all these just have to be the negative of what we had for E2U. And so at this point, we can cross this one off. And we've amazingly finished this whole business, and we've derived the character table. And remember, all of this is with the definition of epsilon being equal to e to pi over 3i, or some character tables will write it 2 pi over 6i. You can see how this 2 pi over 6 emphasizes that principal rotation axis is a C6 and C6h. So that's where this ends up all coming from. But we can go to what you might find online and basically see that we've derived this entire character table correctly. If you check all this now, the ordering that you list these vectors, right, like within E1G, if I were to put this top vector below, that's fine, right? There's nothing wrong with that. We didn't explicitly show that this bottom vector, for example, is x minus iy, but it ends up being that you get the complex conjugate, and that's sort of how this works. But yeah, very complicated character table, but we satisfy our character table rules. That's the key thing that are always true. We have 12 ones here. We have 12 irreducible representations, even though we call them by Mulliken symbols, grouping them together. Strictly speaking, we have 12 vectors here because we have 12 classes. So yeah, I hope that got something out of this long derivation.